All right, we are back. It is Calc 1. We're looking at Chapter 5. We're doing 5.3, the fundamental theorem of calculus. Nice. So 5.3 starts on on page 18 in the Chapter 5 packet. So go to page 18 and let's take a look. We've discussed two major branches of differential calculus, the tangent line problem, and integral calculus with the area problems. The connection between the two branches was discovered independently by Newton and Leibniz. The connection is the fundamental theorem of calculus. And so finding the exact area under a curve and or the slope of the tangent line, the instantaneous slopes on a curve. So this is what it says basically. The fundamental theorem of calculus, halfway down page 18 here, we're saying from A to B, f of x dx is equal to f of b minus f of a. That is the upper limit minus the lower limit. And so mathematically, they will work out to be the same. When we have a definite integral with numbers for bounds, we don't use c for constant anymore. And it says why, because mathematically they will work themselves out, kind of. So on the little y question, it's mathematically they work themselves out. And I'll show you that on 1, but then after that we just kind of disregard it. So let's look at the example on page 18. We've got from 1 to 2, the integral from 1 to 2 of t cubed minus 9t dt. So we do the integration, so we do this, that is t to the 4th. Remember, we add 1 and then divide by whatever power we have there. Add 1. That's a square, divided by 2. And then we say plus c. But now this is a definite integral. So we're going from 1 to 2. So we do the upper minus the lower. So if we do the upper minus the lower, what that's going to look like now is I'm going to put 2 in everywhere where there's a t. And so I have 2 to the 4th over 4 minus 9 times 2 squared over 2 plus c minus, and then I'm going to put 1 in everywhere there's a t. 1 to the 4th over 4 minus 9 times 1 squared over 2 plus c. And now you're going to see why we just disregard the c in a definite integral. So what do we end up with here? What is that? That's 16/4. So that's just 4 minus one of those 2's die, 18 plus c minus 1/4 minus let's call it, instead of 9/2, let's call it 18/4 plus c. And so all right, so what is that? 17/4. What are we doing here? We got negative 14 over 1 minus, plus c, minus, sorry, minus 17 fourths, but then plus 17 fourths, minus c. So we did the distributive. I combined those two, got 17 fourths, and then negative, and the negative is a positive, and the negative on the c. So the c's cancel off. And then I got to get this into fourths. So what are we looking at here? Times 4 is 4, negative 56 fourths. And then the plus c and the minus c die, and then plus 17 fourths. So 39, negative 39 fourths. And there is that's what it turns out to be. That is the exact area under that curve from 1 to 2 is negative 39 fourths. And we'll talk about why, how that could be negative as we continue. All right. But this was more or less about this answer and more about why we disregard C. Every time you do the upper minus the lower, you're going to end up with a plus C and then a minus C, and then the C's just go. So when you have a definite integral, you don't need the constants. All right. Okay, what happens with absolute values such as draw the graph and integrate? Okay, we can do that. So we're on page 19. Let's take a look. At this. So we're doing the absolute value. So that is plus or minus 2x minus 1 dx. So what does that mean? Well, if we take a look at the picture of the absolute value of this guy, here, let's look at f of x is equal to the absolute value of 2x minus 1. So what would that do? That would mean at 1, it would be 2 1/2. So this would just basically be y is equal to 2x minus 1, and y is equal to the opposite of that. So negative 2x plus 1. So negative 2x plus 1 starts at 1. I go down 2 and over 1. And then put another dot. And so we get this line. All right. This line starts at negative 1. I go up 2 and over 1. And that looks like this. All right. And they want it from 0 to 2. We'll put the 2 there. And so we want this area. We want this area right here and this area right here. And again, if we wanted to do this without calculus, this part, we don't care about that. That was just to draw my lines. We could do this one without calculus because we know this is 1.5, this is 1/2. And so without calc, we could just say 1/2 times 1 times 1/2, that's that area. And 1.5 times, we pop the 2 in there. That's 3 up there, so 2 comma 3. And so we'd know that area, and then we just add them up. And that would be that. But we're doing it with an integral, with calculus, so we're going to kind of split this into 2 integrals. So we're looking at the positive part, the 2x minus 1, this part, is going to be just from 0 to 1/2. So we're breaking this integral into 2 integrals now. We're going to say from 0 to 1/2, we're going to work with negative 2x plus 1. That's this guy. Oh, I'm sorry, that's this guy. And then that's this guy. All right, so dx and then plus the integral from 1/2 to 2, and that's going to be this line, which is this guy. It starts at -1. So 2x minus 1 dx. And now we just do the integrals. We're going to do both of them. So let's do that. The antiderivative, right? So x squared over 2. You got that -2 out front. Plus 1x from 0 to 1/2. And we'll simplify that. Let's simplify that to be just the opposite of x squared plus x from 0 to 1/2. I think I did that, or did I not do that? I didn't simplify my work, but we'll simplify here. All right, so plus, do that here. This is going to kind of, right, you got 2x squared over 2, because whatever that is goes down, so the 2's are going to cancel. Minus x, and that's from 1/2 to 2. So plus, oh, don't put a bracket on there, though. It's just a straight up and down line. Sorry. You do a bracket if you have the whole thing bracketed off. Otherwise, it's just a straight up and down line for definite integrals like that. If you're going to have the whole thing in brackets, then you can make it a bracket like this for shorthand if I was going to bracket them both off. But when it's like standalone, you don't do that. So x squared minus x from 1/2 to 2. All right, so now it's upper minus lower, upper minus lower. And again, on the test, show me the work with the zeros. A lot of times students just say, oh, it's going to be 0, I'm going to zero it out. That's great. You can zero it out, but show at least a step so I know you didn't just disregard that. Plus 1/2. All right, minus, and so show me 0 squared plus 0. And now we can disregard it. Now we know that's 0. Plus, and now we're going to do the 1/2 again. So that's good. Whatever this works out to be, that's going to be the same as this. Half. Oh, no, it's not, because we don't have a negative on it. Never mind. That's not going to be the same. Silly. So, again, upper minus lower. So that should have been the lower. Goodness gracious, so many little mistakes here. 2 squared minus 2, and 1/2 squared minus 1/2. There we go. So what is this? It is the opposite. So you do the power first, that's 1/4, and then crank the negative on it. So it's -1/4 plus 2/4. And then the zeros are gone, plus 4 minus 2, which is just 2, minus, and again, that is 1/4 minus 2/4. That's -1/4, but it's minus a -1/4, so plus 1/4. All right. Well, it looks like those 1/4 are going to die, and I got 1/2 plus 2, or 2.5. So that area is 2.5. We could confirm that with just our geometry. We could have just said 1/2 times 1 times 1/2, 1/2 base times height for the triangle, and 1.5 times 3 times 0.5, and then add them up, and that'll come out to be 2.5. So there we have it. Let's take a look. The mean value theorem for integrals. So what does the mean value theorem for integrals mean? Let's look at that. So the mean value of integrals, if f of x is continuous on the closed interval a to b, when there is at least one point C as an element of AB such that f of c times b minus a, by using the mean value theorem, we find the average. There's at least one rectangle over AB of some height f of c where the area is exactly the area under the curve. All right. So what does that mean? Let's take a look. So fill this in on your line. A to B of x dx. F of c. B minus a. All right. And when we're looking at that, think of it that there's some line here. And we're going from here to there, to there, to there, like that. And so we're going from A to B. And basically it says that there's a C in there somewhere. Where, so there is at least one rectangle over the interval A to B of some height f of c where, or whose area is exactly the area under the curve. Now, this might make a little more sense. I don't know how good my picture was. This might make a little more sense in an actual problem. So let's take a look and see what they're talking about here. So since f of x equals x to the third is continuous on the interval from 1 to 4, the mean value theorem for integrals guarantees that there is some point c such that from A to B, f of x, f of c, b minus a, find c. Okay, so let me show you what they're talking about here. I don't know if I'm going to keep that up there. Yeah, maybe we can keep that up there. Or if we should just do it here. Let's do a new picture. Let's do a new picture. So this is page 19, chapter 5, the mean value theorem for integrals. Lots of fun. All right, so remember what f of x equals x cubed looks like. That is a third degree, so it kind of goes like this. And we're looking at the area from 1 to 4. So here, I'm going to stretch this out a little bit. Like that. Just so it fits. So you get the general idea of what that looks like, 1 to 4. All right, so what is going on? Well, let's say that the integral from 1 to 4 of x to the third dx has to equal f of c. So here, let me write this down first. A to b of f of x dx is equal to f of c minus a. All right, so basically what we're saying is this thing has to equal f of c, which is f of x. So just c cubed, so whatever that function is, but with a c on it. And then times 4 minus 1. All right, and so let's see what that looks like. So we're going to do this integral. So that is add 1 is 4, divide by 4. It goes from 1 to 4. We do upper minus lower. So we got 4 to the 4th over 4 minus 1 to the 4th over 4. That is 4 to the 3rd, basically, which is, what do I have there? 4 times 4 is 16, times 4 again is 64. So we got 64 minus 1/4. Oh, okay, I'm looking at my thing. I did, I don't know why I did it that way. 256. I'm trying to follow my work here. We got 4 to the 4th over 4 minus 1 to the 4th over 4. And then I just left it 256 minus 1, 255. I guess. And I got rid of the 4s. I don't know why I didn't get rid of the 4s. On the board, this is how I did it on the sheet. Maybe on the sheet it's easier? I don't know. 256 over 4 minus 1 over 4. And so then that's just 255 over 4. I guess that's fine. I was going to simplify it. I was going to divide out the 4s and just get a single number. I mean, it would still be with 3/4. So that's fine. This is good. This is good. Let's leave it like that. And then we have that equal to this, which is 3 cubed. All right. So now we divide by 3. We divide by 3. And so now it's 255/12 equals cubed, and then we take the cube root of. 255/12, which is approximately 2.769. And now we have to just show that, okay, this value, C, is definitely within this interval. So there is a point that I can find here in between that will split this into like 2 pieces. The exact area under the curve. So there is at least one point C whose area is exactly the area under the curve. So we found that point where this 2.76 is on that interval, and it splits it into equal areas, and that's the mean value theorem. So and then we just show that that's in between those two. So 1 is less than 2.769, which is less than 4. So it's within the interval, and it's equal spacing. Not equal spacing. It's not exactly, the areas are the same. So if I pick an area close to 3, then this area and this area, which is going way up, is going to be the same. All right. Yeah, I don't know how that came across, but hopefully you understand it. Definition of the average value of a function on an interval. If f is integrable on the closed interval a to b, then the average value given by the mean value theorem of f on the integral is 1 over b minus a times the integral. So that's the definition of the average. If we just take this minus this, put it on the bottom, and then multiply it by the integral, you'll get what we consider to be the average. All right? And I think that is all. Let's look back at the first page. The next one. 5.4. Oh no, not Not there yet, huh? 2 more pages. Sorry, 2 more pages. What are we doing for time? Okay, we're doing okay. Let's look at page 20. Theorem 5.5. That's what's confusing with the note packet. We've got the theorems and the sections are all very, very close. So I thought maybe we were going on to the next section, but we are not. We're still on same section, still 5.3. So theorem 5.5, the fundamental theorem of calculus, part 2. Oh boy. So the relationship between differentiation and integration when you first integrate and then differentiate. So what does that mean? That means if I do the derivative of the integral, I will end up back with the original function. So if I do the derivative of the integral, we're right back to the original function. You do the innermost first. So we would do this first, and then we'd take the derivative of it, and then we'd end up right back with f of x. And we can show that with examples. So examples using the second fundamental theorem of calculus. First take the integral, and then the derivative. So let's do it. And we should end up exactly with what we started with. So number 1, f of x is equal to the integral from 0 to x of t times t squared plus 1 dt. So we want to do a quick rewrite on that. T cubed plus t dt, and then integrate. So add 1, that's t4, divide by whatever the power is, 4. Add 1, that's t squared, divide by the power, and go from 0 to x. So what is that going to look like? Well, I'm going to do upper minus lower. So I'm going to put in x everywhere, x to the 4th over 4, plus x squared over 2, minus, I'm going to put in 0 everywhere, 0 to the 4th over 4, plus 0 squared over 2. So that all just goes to 0. So we just have this. So that is our integral f of x. We'll put a little capital, so it's a general formula. As we would say, in the normal circumstance, we would say plus c, but since it was an integral, they gave us a definite integral. So there's a 0 and an x, so it's kind of a rock and a hard place. It doesn't matter though, because if I put plus c, I would just take the derivative of c as 0, and it would be gone anyway. So now let's take the derivative of that. So the derivative of this, 4 times that, it's 4/4, x to the 3rd, plus 2/2 x. And then simplify. And so we end up with x to the 3rd plus x, which is exactly what we started with in terms of t. All right. Let's look at example 2. So example 2 is 0 to x of cosine t dt. So we want to do, I don't have to rewrite anything there. That would just be the sine. Remember, it's the antiderivative, so that's why it's not negative sign. We're going the derivative of what gives me cosine, so that's sine t from 0 to x, and then upper minus lower. So the sine of x minus the sine of 0, which does happen to be 0. So that's just sine x. F of x is equal to the sine of x. And then if I do the derivative, that is the cosine. So d dx of that and d dx of this, we end up with just what we started with. All right. Let's take a look at those pictures. What's going on with the pictures? F of 0 is 0. So what does that mean? Well, they've got the cosine curve. So we're looking at the area of the cosine curve. That's the cosine of x, and they want us to show f of 0 is 0. So on the integral, that would be 0 to 0 of cosine dx, which we don't have to do any work there. That's just when that number matches that number, it's automatically 0. All right, so f of x equals sine of x, and you obtain these. All right, so these are integral. So again, this is the cosine of x to where x is equal to pi over 6. So what do they want us to show? They want us to show from 0 to pi over 6 on cosine of x dx. What do we end up with? Now they're telling us we should end up with 1/2. So let's make sure that that's what that does end up with, right? Pi over 6. So we would do the sine of pi over 6 minus, that's upper minus lower. So I did the integral, and I'm just subbing it in too. And that's the sine of 0, which is 0. So we're looking at the sine of pi over 6, the sine of 30 degrees. So who remembers there? Remember pi over 6 and pi over 4 and pi over 3. Remember this guy? With sine and cosine. And the 1, 2, 3, and 3, 2, 1, and divide everything by 2, and take the square root of everything. And so the sine of pi over 6 is 1/2, minus 0, which is 1/2. So we're just confirming that they have the answer ready given, so 1/2. And then this is just going to be more of the same for the next one and the next one. I'm just going to write those down. You just write those on the notes. Oh, I just erased my great thing there. Hopefully you remembered all that. So the next one, when we have f of pi over 4, that's going to end up being just the square root of 2 over 2. And I just erased it. It's going to just always shake out to be this again and again and again. So it would be the sine of pi over 4 minus the sine of 0. We just change that to pi over 4. And so we'd end up with the square root of 2 over 2. So from 0 to pi over 4 of the cosine of x dx, that's going to equal that. And then the last one, from 0 to pi over 3, 60 degrees, right? Cosine x dx, that's just going to equal the square root of 3 over 2. So I just had that right there and I erased it. But again, all we're going to do is change that to pi over 3, and then that's going to change to pi over 3, and then that's going to change to the square root of 3 over 2. And that's still going to be minus 0. So that's for the last picture. On page 20, all right, you can think of function f of x as accumulating the area under the curve f of t equals cosine t from 0 to x. And so f of pi over 2 would just give you 1. The accumulated area under the cosine curve on the entire interval from 0 to pi over 2. This interpretation of the integral as an accumulated function is often used in applications of integration. All right, so voila. Let's take a look at page 21. So page 21 has us doing a bunch of definite integrals from 0 to 3 of x plus 1 dx. And again, these are actually pretty quick. You add the power, so it's 1 plus 1, that's 2. Whatever that power is, you divide it in the denominator. And then that becomes an x, and then we go from 0 to 3, and then it's upper minus lower. And we just pop it in, 3 squared over 2 plus 3 minus 0 squared over 2 plus 0. And that goes to 0, that's 9 halves, plus 6 halves, that's 15 halves. Number 4, we're looking at from 0 to 2, the square root of x cubed. So let's do a quick rewrite. X to the 3 halves, like that. And so remember, when we do the antiderivative of that, we're just adding 2 halves, or whatever that is, to the top. So 5 halves, and then whatever that is, whatever this power is, it's going to be the reciprocal as the coefficient. Because I'm dividing by 5 halves. So if I divide by 5 halves, it's the same as multiplying by 2/5. So that's the easiest way to do that. And then we're going from 0 to 2. So what does that look like? Again, upper minus lower. And so we get 2/5 of 2 to the 5 halves minus 2/5 0 to the 5 halves. And so that's just 0, and this is kind of a mess. What is that? I guess I could just say it like that. Here, 2 to the 5th is 32, or how do we want to do this? It's the square root of 2 to the 5th. 2/5 square roots of 32, I guess. And then that's really 16 times 2, right? So 4. So 2/5 times 4 over 1 times square root of 2. Or 8/5 square root of 2. You could probably just lay it like this. I mean, we're not really worried about this stuff right now, but that's fine. If you simplified it down, that's fine. If you just left it like this, that would be fine. I think on the key, I just left it like that. All right, let's look at the next one, cosine. And we just did those to death on the last page, so let's see what we got going on here. From pi over 2 to 3 pi over 2, cosine of x dx. So when we integrate it, it's the sine of x going from pi over 2, 3 pi over 2, and we do upper minus lower. So we've got the sine of 3 pi over 2 minus the sine of pi over 2. Alrighty, so what is that? The sine of 270 is -1. And the sine of 90 is +1. And so we end up with -2. And again, we will examine how we're getting integrals where it's negative. It's just basically the area underneath the x-axis is all, instead of above the x-axis. But we'll explore it into the future. So that's not wrong. -2 is correct. And I'll remember, I guess I didn't remember coleslaw. And 0, -1. So, right, so the sine of 90, oh wait, I got those mixed around though. You got to make sure you know how to put a point down. 0, 1, door, 0 right or left, 1 up, and 0 right or left and 1 down. So there's our pi over 2 and 3 pi over 2. All right, let's get the last one in this little section from 1 to 4. Of 1/2 x dx. All right, so then remember you add 1, so it's a 2. And so now there's already a 2 down there, but now we had to add another 2 down there. So that should be 4, right? So we're doing x squared over 4 from 1 to 4. Definite integral, upper minus lower. And so we got 4 squared over 4 minus 1 squared over 4. So that is 16/4, or 4 minus 1/4, which is what, 3 3/4? Or if you went 16/4. I should have just left it 16/4. Minus 1/4, and then call it 15/4. That's fine. This is fine. This is fine. Either way. Same thing. All right. Let's see. Sketch the region whose area is represented by the definite integral, and find the area by evaluating the integral and by using geometry. Okay. So let's get rid of this and do this. Oh, twice. We get to do this twice. Oh, boy. Oh, boy. Just like Mickey Mouse. All right. So what are we doing here? We got from 1 to 3 of 4 dx. So if I think about that, f of x is equal to 4, or y is equal to 4 from 1 to 3. So this, I really wouldn't need calculus to do this one. 1, 2, 3, 4. That's a horizontal line at y equals 4. And from 1 to 3, it's this little rectangle. That's basically 2 by 4. So since we know that's 2 by 4, area is equal to length times width of a rectangle. So 2 times 4 is 8. All right, so that is without calculus. So let's look with calculus. So with calculus, I do the antiderivative. That's 4x. I take it from 1 to 3. I do upper minus lower. And I get 4 times 3 minus 4 times 1. That's 12 minus 4, which is also 8. Yay. Let's do another one. That was so much fun. So we'll do it geometrically. We got 0 to 4 of x plus 2 dx. So again, using just geometry, you got to remember y equals x plus 2. You got to remember how to graph a line. We go to 2, that's our starting point. We go up 1 and over 1. And they want 0 to 4. So let's go up 1, over 1. Up 1, over 1. Up 1, over 1. So there's our line, but they want it from 0 to 4. And so there's a couple of ways we could do this. It's a trapezoid. So you could say base 1 plus base 2 times 1/2 the height. That's one way to do it if you want to do it with a trapezoid. And if you forgot about trapezoids, that's okay. This is easy to do geometrically this way too. You can break it into a rectangle that's 2 by 4 and a triangle that's 4 by, how far up did 1, 2, 3, 4, 4 by 4. Yeah. And so then we'd say the area of the rectangle, 2 times 4, that's 8 again. And then the area of the triangle, that's 1/2 base times height. So area of the triangle is half of 4 times 4, which is also 8. And then we would take those two areas and add them together. So 16 square units. All right. Let's do it with calculus. Now again, we could have streamlined this and just used the area of a trapezoid, which is 1/2 height times base 1 plus base 2. And then it wouldn't have been that complicated. So this would have been base 1, 2, and that would have been base 2, 6. So we would have said 2 plus 6 times the height, 4, and then half. And we'd still get 16. All right, so back to here. What are we doing? We're doing the antiderivative of that. So that's x squared over 2 plus 2x. On the definite integral from 0 to 4, upper minus lower. We got 4 squared over 2 plus 2 times 4 minus 0 squared over 2. It's 2 times 0. And so that all goes to 0. This is half of 16 is 8 plus 8, which is 16 square units. So, maybe a little less hassle. And again, on the test, make sure you show me the 0 part. I have to know that you understand it's always upper minus lower. Sometimes this lower disappears when there's a 0. Sometimes, depending on what your integral is, that won't disappear. Sometimes there's like +1 or something in there, and it doesn't go away. And so that's a habit you have to not get into of just disregarding zeros. I need to see that work. All right. And that is it for 5.3.